Hello student, in the last lecture I have discussed about the instrumentation of IR spectroscopy. Okay, what are the different parts of IR spectrometer and how they work? I have already discussed the working principle of IR spectrometer. Okay, so basically by IR spectroscopy we identify by IR spectroscopy we identify the functional group, and groups are present in a molecule or chemical compound. Okay, so we identify the functional group or groups which are present in a chemical compound. So to identify the functional group of chemical compound in we use IR spectroscopy. Okay, and to perform IR spectroscopy technique we use a specific range of electromagnetic spectrum that we call as IR radiation. Okay, so basically what we do, so first whatever sample we want to analyze, that sample may be in the form of solid, or maybe in the form of liquid, or in the maybe form of gas. Okay, so first we prepare the sample and put it in the IR spectrometer. Okay, then so what is IR spectrometer? IR spectrometer is the instrument that is used in IR spectroscopy to analyze the sample, to identify the functional group of the sample. Okay, now what is the principle of the IR spectrometer? So after placing the sample in IR spectrometer, there is a source present in the IR spectrometer, and this source produces IR radiation due to the electrical heating. Okay, and this produced IR radiation are lights of different wavelength and travel in the form of photon energy packets. Okay, so when this IR radiation fall on the sample, when this IR radiation fall on the particular sample or the sample which we want to be analyzed, the interatomic bonds of the sample or the molecules, that is interatomic bond means the bond between the atoms, known as interatomic bond. Okay, so when this IR radiation fall on the sample, the interatomic bonds in this molecule, that is bond between these atoms known as interatomic bond, these interatomic bonds absorb the energy of IR radiation. Okay, and when this bond absorb the energy of IR radiation, they start vibrating. Okay, these vibrations are of different types, such as stretching and bending vibration. We have already discussed this vibration, these types of vibration. What is stretching vibration, what is bending vibration. Okay, so when the interatomic bond absorb the IR radiation, they start vibrating. These vibrations are of different types, such as stretching and bending vibration. Okay, we know IR is composed of a range of different wavelength. Okay, so IR radiation is composed of a range of different type of wavelength. In IR radiation there are different type of wavelength are there. So it is not necessary that sample molecules absorb light of every wavelength. Okay, they absorb light of specific wavelength. Okay, so they do not absorb the light of every wavelength. Okay, so they absorb light of specific wavelength. Suppose for example, let's if 100, 200, 300 and 400 as wavelength of different light. Okay, so suppose when these lights that means 100, 200, 300, 400 of wavelength of light fall on the sample which we want to be analyzed. It absorbs light of wavelength 400. Okay, so if 100, 200, 300, 400 wavelength of light fall on the sample, that means that means this sample which you want to be analyzed, those 100, 200, 300, 400 wavelength are fall on the sample, it absorb light of wavelength only 400 and apart from that. Okay, and the other remaining lights of like 100, 200 and 300 wavelength, it does not absorb them. Okay, that means these lights transmit through the sample without absorbing. That means 100, 200, 300 wavelength transmit through the sample without absorbing. Only 400 wavelength is absorbed. Okay. Since no absorption occur of 100, 200, 300 wavelength light. Okay. Completely 100% transmission happens for 100, 200, 300 wavelength. Okay. This transmitted light is detected by a device known as detector, which is present inside the spectrophotometer. Okay. Detector detects transmitted light and based on this detected light, spectrum is generated, that is graph is generated, and that we call as spectrum. Or spectrum, the generated spectrum is like this. Okay, so on y-axis, that means this axis, so on y-axis of spectrum we have transmittance which represent the transmitted light, and x-axis, that means this axis, we have wavelength or wave number. Okay, so this light of wavelength, that means 100, 200, 300, these are not absorbed by molecule and they are transmitted 100%. So on the graph, if this 100% transmitted, so if on the graph, if this light means 100, 200, 300 is 100% transmittance, and if wave number is given on the x-axis, that means 100, 200, 300 is in this x-axis. So here 100, 200 on the spectrum, the light that does not absorb show up straight lines here on this graph, means this portion is 100% transmittance of 100, 200, 300 wavelength. Okay, so this line are the lines of transmitted light which are not absorbed by the sample molecule. Okay, so this is our first point. That means here 100, 200, 300 light are fully transmitted, that is show straight line, and 400 wavelength is absorbed by the sample, that's this 0% transmittance. Okay, now coming to the second point, that is after absorbing the energy, the interatomic bonds of sample molecule starts vibrating. Okay, vibration are of different types. Okay, such as stretching and bonding. Okay, so we have already discussed vibration are different type, and that is stretching, two types, stretching and bending. This stretching and bending is again classified into two types. Okay, so after absorbing the energy, the interatomic bonds of sample molecules starts vibrating. Vibration are of different types such as stretching and bending. Okay, so this is another important point. Okay, so it is not necessary that molecule absorb only one specific type of wavelength. Suppose if light 500 falls on this sample, then this band shows bending. Okay, so it is not necessary that molecule absorb only one specific type of wavelength. Suppose if light 500 falls on this sample, then this bond, this interatomic bond, shows another type of bending. Okay, that these bonds can show different types of vibration on different types of wavelength. Okay, so these bonds show different types of vibration on different types of wavelength. It is not fixed. Okay, so it is not fixed that one type of bond will only absorb one type of wavelength. Okay. So it is not necessary that molecules absorb only one specific type of wavelength. Okay. Suppose if light 500 wave falls on this sample, then this bond shows bending also. Okay. That means that these bonds can show different types of vibration on different types of wavelength. Okay. So it is not fixed that one type of bond will only absorb one type of wavelength. Okay, and will have only one type of vibration. So that means that these bonds can show different types of vibration on different types of wavelength. So it is not fixed that one type of bond will only absorb one type of wavelength and will have only one type of vibration. Okay. So let's assume that one bond stretches on 400 wave number and these bands on 500 wavelength. Okay, then when you look at spectrum on x-axis on 400 and 500 wavelength, that means one bond stretch 400 wave number and bending on 500 wavelength. Okay, so then when we look at spectrum on x-axis on 400 and 500 wavelength, we will see peaks of absorption because this light are absorbed by molecules in the sample and hence transmittance will be loss. Okay, or less. Okay, and detector will detect less amount of transmitted light. So here for example on 400 wavelength on x-axis we see only 20% transmittance. Okay, 20% transmittance on y-axis because 80% light was absorbed by the sample, and similarly for 500 we see 30% transmittance. Okay, so after absorption sample molecules vibrate and vibration occur in this manner. Okay, and we get the spectrum from the detector detects this vibration. Detector detects the intensity of light which passes the sample and forms the spectrum in the spectrometer or in the recorder. Okay, so in the next part of this lecture I will discuss details every part of IR spectrometer. Okay.